In this lesson, we're going to check out to see if a function is differentiable. So first, I want to take a look at just some examples of graphs. What does it mean when something is differentiable? Well, there's so many different ways that you can say or use the term derivative. Like, hey, I have an equation that's the derivative. I'm going to differentiate this function. I need to derive the function that I have. And is it differentiable? All differentiable means is, can you take a derivative at every point on the graph? Well, so there's two underlying things that we need to pay attention to here, and those two items might be this. One is a continuous. You can't have something that's differentiable if it's not continuous. If there's a break in the graph or a hole in the graph, there's no slope at that hole. Second thing is it a smooth curve? And here's really what it is. This is my way of saying it. If you have a smooth curve, that will be differentiable, but the official definition is, does the slope from the left-hand side at every point approach the same value as the slope from the right-hand side? It's almost like that definition of limits. For a limit, the limits have to approach the same value from the left to the right. For differentiability, they have to approach the same slope. So, first example up here, we've got that top left example. Is it continuous? You betcha. Is it a smooth curve? Well, it's not much of a curve, it's kind of a straight line, but it is smooth. There's no corners or cusps. It is a differentiable function. Now, another way of looking at it is this exact same thing. We've got two lines, they're matched up in about the same spot, and it is continuous, but is this a smooth curve? No. So that is not differentiable. I'll tell you why. It's not differentiable at the corner. We've reviewed what makes something differentiable. That just tells us. Same thing down here. This is continuous and it is smooth. This one is, it's not continuous. It would be smooth. The slope from the left-hand side at this point approaches the slope from the right, but it's not continuous, so that will not be a good differentiable function. So one of the toughest things we have to figure out is if something's differentiable when you only have the equation. Piecewise functions are particularly tricky. For any polynomial, you know, they're always continuous, they're always smooth. Other functions, you'll have a restricted domain maybe, or you'll know by the function an absolute value function has a corner. But these are the tricky ones. So let's go back to our two questions. Is it continuous and smooth? And so here's what we need to do for this problem. Are they actually equal? If it's continuous, I should be approaching the same value from the left and from the right. Well, if we're approaching from the left-hand side, we're going to use the equation when x is less than 2. Right-hand side, greater than 2, we're going to use the one that says greater than 2. So we plug in the numbers, we see 5 equals 5. Wow, they're approaching the same value. Turns out they are continuous. How do you check smooth? Please check and see, are there derivatives approaching the same value? So I'm literally going to take the derivative of both pieces of that function. The derivative of x squared plus 1 is 2x, and the derivative of 4x minus 3 is 4. So plug in those limits now to those derivatives and see that they are equal to each other. It is smooth, it is continuous, this is differentiable. At every point on this piecewise function. Another example, notice I've changed the function from f to g, and I changed these. Another example, let's see if this one's differentiable. Is it continuous? Is it smooth? Are the functions approaching the same value on the left and right? Are the derivatives approaching the same value on the left and right? As we can see here, the actual functions approach the same value, but the slopes are going to approach something slightly different. They're close, but they're not quite right. Therefore, there's going to be a little bit of a cusp there. They are not differentiable. Final example. What if I told you h of x is continuous? It is differentiable, I know that. What would the values for a and b be equal to? I had to use systems of equations here, but those are the values if h is differentiable.